Hello everyone, I'm Zhang Jiangyi from Harbin Engineering University. Today I will share the research result of our team, titled Sound Attenuation in High Mach Number Oscillating Bubble Media. We studied theoretically and numerically sound attenuation in bubble-containing media. When the bubbles are freely oscillating at high Mach numbers. When the bubble oscillates at a high Mach number, radiation damping, which is directly related to Mach number, becomes the main damping component affecting sound attenuation. We expand one of the main forms of bubble-related acoustic damping factors by extending the previous theory to higher Mach numbers. Further improves the theory of nonlinear sound propagation in bubble-containing media. A nonlinear sound propagation model incorporating second-order liquid compression terms is developed, expressing the sound velocity and density in the media as a function of the driving pressure and taking into account the higher-order liquid compression effects on sound propagation. I will provide a detailed explanation through the following 5 parts. Let's start with the introduction. The violent expansion and collapse of sound-excited bubbles is a hot topic, and many authors have conducted extensive research on the oscillating bubbles with high Mach numbers. It has broad applications in the fields of sonochemistry, medicine, and hydroacoustic. For example, underwater explosion bubbles may cause serious damage to nearby structures, such as ships or submarines. Cavitation bubbles will erode the surface of structures when they burst, and can be used to clean various complex surfaces. And in the above cases, the propagation of sound waves in the medium is significantly affected by the bubbles oscillating at high Mach numbers. There are many theories of sound propagations in the liquid-containing bubbles. And Foddy presented a seminal theory on the interaction of sound waves with bubbles. And in 1968, Weingarten proposed a heuristic mixed medium model, which was later extended by the groups of Cavendish to obtain the equivalent equation of sound propagation in a bubble-containing liquid under nonlinear conditions and to propose the mass and momentum in a bubble-containing liquid conservation equation. And based on the Foddy's methods, Commander and Prosperity proposed a linear model of sound propagation in bubble-containing liquids. However, this model overestimated the sound attenuation under resonant conditions. Louis Nard studied the nonlinear attenuation effects of inertial cavitation bubbles on the sound waves based on Rayleigh-Placet equation, and derived the nonlinear attenuation coefficient through the energy conservation equations, which is several orders of magnitude higher than the classical linear prediction of Commander Prosperity. Later, Jamshidi and Bracknard extend the Lewis-Nard models by using the Km equations instead of the RP equations to describe the compressibility of liquids. Soderhood and his colleague established a model considering completely nonlinear bubbles oscillations, using the Km equations to calculate the radial motion of the bubbles and calculated attenuation and sound velocity in the bubble-containing medium. And in order to calculate the attenuation and sound velocity in bubble liquid more accurately when the bubble wall Mach number is high, a nonlinear sound propagation model including high-order Mach number terms is established in this work. And the expression of sound velocity and attenuation in bubbly water media are derived. By extending the previous theories to higher Mach numbers, the nonlinear model established in this paper expands the form of bubble radiation dampings, which is one of the main factors affecting the sound attenuation. Fully considering the influence of liquid compression on sound propagation, the proposed model has higher accuracy for the calculation of sound attenuation in the medium, especially when the bubble wall Mach number is high. And firstly, we go to the theoretical model. And here we make a series of reasonable assumptions. For example, liquid containing the bubbles is a homogeneous medium with an average pressure and an average temperature. All bubbles are the same size and the bubble interaction are ignored. The gas in the bubbles is ideal and the thermodynamic change per size of gas is isentropic and adiabatic. The bubble remains spherical and oscillates violently under strong sound excitation. So the bubble wall Mach number is high and the compressibility of the liquid needs to be considered. And based on the three fundamental conservation law and the radial vibration equations of the bubbles, we established a sound propagation model containing high-order Mach numbers in medium containing bubbles, and finally obtained the sound attenuation and velocity in the medium related to complex wave number. And part 3 is a model validation. Under the limit condition of the low Mach number of the bubble wall, the sound velocity and the attenuation in the bubble containing mixed liquid are simulated in the linear region and nonlinear region, is respectively to verify the accuracy of the model. We start with the model validation in the linear region. Under low amplitude conditions, the proposed model is used to calculate the sound attenuation and sound velocity and attenuation. And here are the results, and the commander property models provide under the condition of small amplitude is selected as a comparison. They have good agreement. As the frequency increase, the attenuation in the medium first increase and then decrease, reaching the maximum value at the bubble resonant frequency. The sound velocity exhibits a strong dispersion phenomenon under resonant frequency of bubbles. And then the validation of the proposed model will be provided in the nonlinear region, where the bubble oscillates at low Mach number. We should select the appropriate driving pressure and frequency to ensure that the bubble wall Mach number is low, while oscillating nonlinearity. The attenuation and sound velocity are calculated through the proposed model, and the Soja-Hughes model is selected for comparison. And here are the results. They have good agreement. Our model can accurately capture the primary harmonic and subharmonic resonance of the bubbles as well as the fluctuation of sound velocity. And driving by the high amplitude, these peaks all exhibit pressures dependence resonance, and the frequency corresponding to the peak decrease with the increase of the amplitude. As the amplitude increased, the maximum sound velocity in the bubble media increased and the corresponding frequency decreased. And then we go to the results and discussion. And when the bubbles oscillate at high Mach number, the radiation damping, which is directly related to Mach number, becomes the main damping component affecting sound attenuation. At this time, it is crucial to accurately capture the pressure-dependent sound attenuation in bubble-containing media. However, the currently commonly used Soja-Hughes model only focused on the role played by the first-order Mach number terms, while ignoring the effect of the higher-order compressibility of the liquid on the sound attenuation. And in this section, we show the difference in the attenuation between the proposed model and the Soja-Hughes model. And since the bubble wall Mach number is an important factor affecting the attenuation, we also investigate the difference between the bubble wall Mach number calculated by the two models. We start with setting the appropriate driving amplitude and frequency to make the bubbles oscillate at high Mach number. The larger the driving amplitude, the stronger the nonlinear effect, and the greater the impact of Mach number related radiation dampings on attenuation. The higher the driver amplitude, the greater the difference of the attenuation calculated by the two models. The greater the maximum value of the attenuation difference, and the greater the half qualitative factors of the curve. And here, the half qualitative factors is defined as the corresponding frequency bandwidth when the right curve falls into the maximum value to square root of 2 over 2 times. At the same driving frequency, the difference between the maximum bubbles wall Mach numbers are calculated by the two models increases with the increase of the amplitude. When the driving amplitude is the same, it decreases with the increase of the frequency. Under the nonlinear condition, the sound attenuation in the medium is related to the complex wave number. According to the expression of the real and the imagined part of the square root of the complex wave number, it can be known that the bubble volume factor beta is an important factor affecting the attenuation. Considering the expression of the bubble volume fractions, beta equals to 4 over 3 multiplied by pi r cubic ng. Both the radius of the bubbles r and the number density of the bubbles ng can affect attenuation. In this section, varying the bubble radius and bubble numbers density respectively, the difference between the proposed model and Soldier-Hoo's model in capturing the pressure-dependent attenuation is calculated. Under the same driving amplitude, the half qualitative factor of the curve does not change with the bubble's numbers density. This is because the model established in this paper assumes that each bubble is independent and the vibration states will not be affected by the sound field radiated by other bubbles. Then we go to the conclusion. And in high Mach numbers oscillating region, the proposed sound propagation models has higher accuracy than the nonlinear models considering only the first order Mach number. Second, the higher the driving amplitude, the stronger the nonlinear effect, the more important the radiation damping of the bubble becomes, and the more negligible the nonlinear attenuation associated with the higher order liquid compression effects. In this case, it is necessary to apply the proposed model to calculate the pressure-related attenuation. And third, under the same external driving conditions, the smaller the bubble's radius, the stronger the nonlinear effect, and the more necessary it is to apply to the proposed model to calculate the pressure-dependent sound attenuation. Without considering the coupled effect between the bubbles, the half qualitative factors of the curves, which is related to the difference in attenuation of the two models, is not affected by the bubble number density. Finally, our model can also capture the pressure-dependent resonance of bubble related to higher order liquid compression effects. And thank you for your attention.